In this video, we will learn about the Shepherd's lemma and how to use it to derive the Hicksian demand function from the given expenditure function. So Shepherd's lemma tells us that the minimized expenditure function becomes Hicksian demand function, what we call also the compensated demand function, when differentiated with respect to the price of one of the good. Okay, so basically, if we are being given a minimized expenditure function, okay, so we can find out the Hicksian demand function. Let me write it as HDF using Shepherd's lemma. Okay, so let me write it here, SHEPARD, Shepherd's lemma. Okay, given a minimized expenditure function, we can derive the Hicksian demand function using Shepherd's lemma. Okay, so let us say we are being given a question, that is, suppose a person's expenditure function is being given as E, which is expenditure, which is a function of price 1, price of good 1, price of good 2, holding utility constant, which is equal to U bar P1 into P2 divided by P1 plus P2, where P1 and P2 are the prices of good X1 and X2, and U bar is the fixed utility. We have to derive the Hicksian demand function for good X1 and X2 using Shepherd's lemma. Okay, so as I have told you, the minimized expenditure function becomes the Hicksian demand function when differentiating with respect to prices of one of the good. Okay, let me write it here. What we are being given? We are being given the expenditure function, that is E, which is a function of price of good 1, price of good 2, holding utility constant, which is being given as is U bar times P1 into P2 upon P1 plus P2. Okay, so given this expenditure function, we can find out the Hicksian demand function, that means HDF. Let me write it in short, Hicksian demand function, what we also call the compensated demand function, and let me write it here. So compensated demand function. Okay, how do we find? Simply let's denote x1, and let me write it here, x1 superscript h, which denotes the Hicksian demand function for good x1, will be equal to the partial derivative of expenditure function, okay, with respect to P1, and let us actually derive it. So our x1 will be equal to x1 h, that means Hicksian demand function, will be the partial derivative of this expenditure function with respect to P1, and let's take the derivative here, dE upon dP1 of this function. So first we have u, which is constant, we have nothing to do with this. Then we need to differentiate this expenditure function with respect to P1. Since P1 is in numerator and also in denominator, we use the quotient rule of differentiation here. Okay, so how do we use that very thing here? Let me explain it here. So if we are being given dE upon dP1, okay, will be equal to, let's apply the quotient rule here. So we have u is constant. Quotient rule tells us, if we are being given two functions, let us say h of x is a function of fx upon gx, then the derivative of hx, that is h prime x, will be equal to, first we write the gx, okay, take derivative of f dash fx, so its derivative will be f dash x minus, then we write fx and take the derivative of this denominator function d dash x and divided by gx whole square. Okay, so in place of fx we have p1 p2, and in place of gx we have p1 plus p2, and let's write it here. So dE upon dP1 will be equal to which will be equal to, so we have u dash which is constant, we have nothing to do with this. Then applying the quotient rule, we write first gx, so gx is p1 plus p2, and let me write it here. We have p1 plus p2, okay. Then we write f dash x, that is the derivative of this numerator function with respect to p1, that is p1 p2. Then we subtract and write the numerator function, that is p1 p2, and take the derivative of this denominator function, that is dp1 of p1 plus p2, okay. And divided by p1 plus p2, p1 plus p2 square, which is gx square, okay. So we will be using this very stuff here. So we have here u dash, we have nothing to do with this. Then we have p1 plus p2, p1 plus p2. Now derivative of p1 will be 1, so we will be left with p2 only. Then we have minus p1 p2. Now derivative of p1 will be 1, derivative of p2 will be 0, because we are taking partial derivative with respect to p1, so we will be left with only 1 here, okay. Divide by p1 plus p2 whole square, p1 plus p2 whole square. When solving, we will get x1 h will be equal to u bar. We have here p1 p1 into p2, p1 into p2 plus p2 into p2 is p2 square, minus p1 p2 divided by p1 plus p2 whole square. Na loguniyat, this is bubble bracket, okay. This gets cancelled, we are left with p2 square upon p1 plus p2 square. So I can write it in this fashion, u bar p2 upon p1 plus p2 square, okay. Using, we have p2 square here, p1 plus p2 whole square, and we write it as whole of the numerator and denominator. This square gets here. That is the Hicksian demand function for good x1, okay. Symmetrically, we can find out the Hicksian demand function for good x2, and let me derive that very thing here for x2 also. So x2h, that means Hicksian demand function for good x2 will be equal to the derivative of expenditure function with respect to p2 this time, okay. So given expenditure function is this, so using the quotient rule, so let us say this is our f of this is our g of x, this is our f of x, okay. As I have told you, first we write gx, or let's write the utility first, which is u bar. Then using the quotient rule, first we write gx, that is p1 plus p2, p1 plus p2. Then take the partial derivative with respect to p2 this time of the numerator function, that is p1 p2. Then we subtract and write the numerator function, that is p1 p2, and take the partial derivative with respect to p2 of denominator function, that is p1 plus p2, and we divided by gx whole square, p1 plus p2 whole square, okay. This is the way we derive it. That gives us x2 will be equal to, and let me write it here, x2h will be equal to, so we have u which is constant, Then we have P1 plus P2, P1 plus P2. Derivative of P2 will be 1, so we will be left with P1 only here, minus, we write P1 P2 as it is, P1 P2, and take derivative of P2. The derivative of P2 will be here 1, derivative of constant is 0, P1 is assumed to be constant or taken to be constant because we are taking the derivative with respect to P2. So here we will be left with only 1, okay, and we whole divided by P1 plus P2 whole square, okay, which gives us x2h will be equal to u bar, okay, so P1 into P1 is P1 square plus P1 into P2 is P1 P2 minus P1 P2 divided by P1 plus P2 whole square, 4 square nuki ha. So this gives us, and this term gets cancelled with this, and we are left with u bar. Then we have this thing P1 square upon P1 plus P2 square, and which can be written in this fashion: u bar into P1 upon P1 plus P2 whole square. This is our compensated demand function, or what we call the Hessian demand function for good x2. Okay, this is how we use the Shepherd's lemma in deriving the compensated demand function or Hessian demand function from the given minimized expenditure function. Our minimized expenditure function was this. Okay, we applied the Shepherd's lemma. Okay, we applied the Shepherd's lemma and we got the, we got the Hessian demand function. Here we also got Hessian demand function, or what we call also the compensated demand function. Compensated demand function using Shepherd's lemma. Using this Shepherd's lemma. I hope I make myself clear in this video. Thank you.